Hello, this is Philippe, and today I'm happy to present to you SummaC on revisiting NLI models for summary consistency. Today we'll cover what is summary factual consistency and why it's important. This is a running example for the presentation. On the left, you have a document talking about scientists studying an area of Mars called Arcadia Planitia and the weird shapes that are on its surface. And on the right, you have a model-generated summary. And the third sentence of the summary says that Arcadia Planitia is an ideal place for future missions. However, this was never mentioned in the document. And this is an example of an inconsistency in a summary where the fact in the summary that's stated is not backed or not aligned with what's said in the document. You can see how it's important as we start using these summarizers in practice, it's important for the summaries produced to be factually consistent with the documents they summarize so the models don't make up facts. There's usually 3 steps to approach factual consistency in summarization. The first one is to collect data sets to see the extent of the problem in current summarizers. The second is to then build models, detect the errors in the data sets collected in step 1. And the third step is to then build new summarizers that avoid or fix these errors. In this talk, we'll focus on the first 2 steps of the process. Let's first look at data sets. So our first contribution is what we call the SummaC benchmark, in which we collected 6 of the largest data sets for consistency detection, and we standardized them to the task of binary classification. We're going to look at the data sets one by one in chronological order. The first data set is CogentSum, or CGS, came out in 2019. And in CogentSum, the authors proposed that summary consistency detection should be a ranking problem in which, given a single document and 2 sentences, one consistent and inconsistent, a summarizer model should put higher weight on the consistent than the inconsistent. The second data set is XSumFaith. The authors first differentiated between extrinsic and intrinsic factual errors, which became a standard in which intrinsic errors are contradicting elements in the original document. However, extrinsic errors are potentially accurate, however, not stated in the original document. The other interesting aspect of XSumFaith is that it focuses on the XSum dataset when most of the other datasets focus on the CNN Daily Mail dataset. The third dataset is Polytope. Polytope is the first of the datasets to introduce a typology of errors. They introduced 5 types of accuracy errors. The fourth dataset is FactCC. Most of the data sets are crowd annotated. However, FactCC is fully expert annotated because the authors found that crowd annotation doesn't lead to high inter-annotator agreement. The other important aspect of FactCC is it contains a synthetic portion of data that was generated through rule-based methods. Synthetic training data can be used for training models because it is a larger data set. SumEval is the 5th data set in the benchmark. It included 23 summarizers when most of the other data sets only included up to maybe 10 summarizers. And SumEval also used a 5-point Likert scale. Finally, Frank is the 6th data set in the benchmark. Frank also introduced an error typology with 7 different types of errors. Frank is the first data set to have analysis both on CNN Daily Mail and XSum. These different data sets have very different characteristics. They were built by different research groups, and therefore they represent a variety of opinions on factual consistency. For instance, here you see in the last column, we report what fraction of the summaries are consistent or have a label of 1. And you can see that it goes all the way from 6% to 90% in SumEval. Because of this, we have to be careful with which metrics we use to measure performance on the benchmark. And we propose to use balanced accuracy. The 3 objectives for the benchmark is first to standardize the task to binary classification across all these data sets and standardize the metrics used. The second is for broader evaluation by seeing which models can generalize across data sets, across settings. And the third is ease of access because we're releasing the data set publicly. Next step, let's look at models for inconsistency detection. There are 2 main types of methods. NLI-based methods first. NLI is the task of determining, given a premise and a hypothesis text, whether the hypothesis entails, contradicts, or is neutral to the premise. And you can see how that could be relevant to inconsistency detection because we want to see if the summary is entailed, contradicting, or neutral to the original document. The second kind of method is QAG-based method, in which we first generate questions through a QG model, and then we see whether the answers to the questions are the same based on the text in the summary and based on the text in the source. Recent work has found that the state of the art lies in QAG-based methods, with NLI-based methods not performing nearly as well as QAG-based methods. But let's take a closer look at NLI models and how they perform. Going back to the example from the start of the presentation, if we feed the entire document as the premise and the entire summary as a hypothesis to a state-of-the-art NLI model, the model gives a 91% probability to the entailment class. You can see how this is a problem because we know that the third sentence here is not supported by the document. Taking the same NLI model and now looking at a finer granularity, where we feed single sentence document with single summary sentences into the NLI models, what we find is much more positive. So first, we find that the first summary sentence is entailed heavily by the second document sentence, and the second summary sentence is heavily entailed by the third document sentence. However, the third summary sentence does not get any high entailment score from any of the document sentences. What we find here is that there is a mismatch in granularity between NLI datasets, which mostly are at the sentence level, and then the consistency detection task, which is at the document level. So this is why we propose our first model, SummaC zero-shot. First, we take the document and split it into blocks. Blocks can be sentences or paragraphs. They can be of various size. We also split the summary into the same blocks. Then we run an NLI model on every single document and sentence block. And we obtain an n by n matrix in which we put one entailment score from document summary sentence pair. And then we, for each column, that means for each sentence in the summary, take the maximum, meaning we take the maximum support for each of the summary sentences. And then we take the mean across all of the summary sentences to obtain a single score, which we'll use for our prediction. So you can see why this model is zero-shot is because there is no trained parameters here. If you have a trained NLI model, you can run this entire pipeline. There are no parameters that you need to train. There are two details that I glossed over. One is which NLI model should we use? And then two is why are we using entailment? Why can't we use contradiction or neutral labels? We'll go over that later in the talk. For now, assume that these parameters are fixed. Looking at the results on the benchmark, SummaC zero-shot outperforms other methods based on QAG or a parsing method or even a classifier trained on the entire FACTCC synthetic data. And it obtains state-of-the-art on the benchmark. If you look closely at each of the data sets, you see that QuestEval, which is the state-of-the-art on several of these data sets prior to SummaC, is still a really strong performer. It achieves highest performance on 3 of the 6 subsets, but overall, SummaC zero-shot achieves the highest performance. One difficulty here is this max operator. There's a lot of loss of information when you take the max out of the entire column. So in our second model, which we called SummaConf, we look at trying to extract more information from the column than just the maximum. So first, we build the exact same n by n matrix. And then the problem we have is that M and N are not fixed. And for each document, there might be a different number of blocks. So what we need to do is build a fixed size representation for each of the columns. And the way we do this is we take all the numbers in the column and we make a histogram with a fixed number of bins. So for instance, if we have 5 bins, then we do a count of all the numbers between 0 and 0.2, and then 0.2 and 0.4, etc. And this gives us a new representation that's h by n, where at least h is fixed. Once we have the histogram, we can run a convolution layer to read this histogram. A convolution layer will have some weights to be trained, even though it's very few weights, it's a learned layer. Once we have the output of the convolution layer for each of the histograms, we can take the average of that and get a single value for the final prediction of the model. So I mentioned that the convolution layer here is a trained layer. We trained it using the synthetic data from the FACTCC dataset. Looking at the results, SummaConf achieves a good performance improvement compared to SummaC zero-shot, increasing the balanced accuracy to 74.4. It now has a larger gap with QAG and parsing and classifier-based models, achieving the highest performance on 4 of the 6 data sets. Let's now take a look at which NLI model should we use and which NLI categories should be taken into account. So first, model selection. We tried different NLI models by varying model architecture as well as the training data set used to see how that affects performance on the SummaC benchmark. We tried 3 different models. First, the decomposable attention model, which is pre-transformers, pre-BERT, pre-training, and then a BERT-based model and a BERT large model. For each of these, we either trained on SNLI, which is one of the first large-scale NLI datasets, or MNLI, which is the follow-up to SNLI and better NLI dataset, or a combination of MNLI as well as vitamin C, which is a very recent NLI dataset. The highlight here is that as NLI gets better, both in terms of model architecture as well as the dataset used, the performance in inconsistency detection goes up. And the benchmark performance was from 56.9% balanced accuracy, which is very close to random chance, to 74%. This is very encouraging because this means that as the NLI community keeps making models better, this should lead to direct performance improvement in the inconsistency detection domain. Second, which NLI category should we use? NLI is a three-way classification task with three classes: entailment, neutral, or contradiction. And what we did is we trained SummaC models with any of the subsets of the labels, either a single one of the labels or any two or all three. And what we find is that entailment-only models perform very strongly. In some cases, including the contradiction label helps a little bit. You can see that in the NLI category, but in general, the neutral category is not useful. In practice, using entailment-only is good enough and it simplifies the model. So this is why we only reported entailment-only models. This kind of makes sense if you think about the inconsistency detection task, not as the task of detecting contradictions, but more about finding support for each of the statements made in the summary. This makes sense because we might expect that intrinsic errors lead to contradiction in the document, but extrinsic factual errors are not supported in documents, so they shouldn't lead to a contradiction. And in this sense, trying to find support and finding an entailment makes a lot more sense. There are a few more experiments in the paper. If you're curious, feel free to check it out, particularly on how to pick the granularity and the block size for SummaC. I want to point out that this focuses on new summarization, but I hope that the community keeps moving towards new domain and summarization, new languages, etc., because factual consistency is a problem, not just in new summarization. Finally, hopefully these are building blocks towards building better summarizers that are factually consistent. And I'd love to talk about any of these topics at the conference. Thank you for listening. I'll be at ACL in person, so please feel free to reach out and let's get coffee. Otherwise, if you're not, you can feel free to reach out by email, go on GitHub and check out the code, put an issue. Thanks for listening.